Hi, I'm Amadou, and today we will see the another method how we can calculate the optimal parameters for the minimum sum of squared error. So we were doing linear regression, and we have seen what is linear regression. Then linear regression is basically to find for the continuous target variable, and it's a supervised machine learning algorithm. So then we are trying to see how we can get optimal parameters for the model linear regressor, or you can say how we can train our linear regressor model. We have seen last in the last session gradient descent. Now we will see another method. So before going to today's session, I want to give just a recap. We have a data set. We were having a data set which is area, price. Okay, just 5 points we have here. This simple a small data set we have plotted a graph of area, price, these variables. We got some points like that. Okay, uh, if I will make, okay, we have points like that. Okay, about 1 2 3 4 5 points we were having. Okay, and here our target is to achieve such a model, to get such a model which should have minimum error. Okay, minimum error. And here we have defined our error as a sum of squared error, which was our actual minus prediction, actual minus prediction, and then we have taken the square so that uh, we can ignore the signs. We are only interested in the magnitude, so we are ignoring the sign. That's why we are taking square here. And for all the points I from 1 to n, so it is our error. We have designed our error function. Okay, so here we want such a line which has minimum SSE, or you can say best fit line. Okay, best fit line or best fit model, you can say. We were having equation of line y is equal mx plus c. Here if we can find our m and c for the minimum SSE, we can say we have find out our parameters for our model. So we have trained our model. Okay, last time we were saying we have designed, we are doing gradient descent. If I will zoom in this one. Okay, now you can see gradient descent we were doing. Okay, so here we were using this function SSE. Let's say SSE is from I to n. Here we have actual which is our y, and prediction y cap and square. Okay, here I will make in this way. I will replace the value of y cap, and I will get this type of equation. Okay, so this type of equation. Now we have this equation, and I am interested to find m and c at the minimum SSE. Okay, where my SSE is minimum. When we have drawn last time a function, if m is on x-axis, as we have two variables, so c on, let's say, on y-axis, and SSE is on z-axis, then if we will plot our graph, okay, for the function SSE, this function will have a graph like that. How we have we come to know that our graph is like that, it's beyond our scope, but actually it is parabolic graph. If you know about the calculus, you may have got an idea of how we have got this graph. Okay, but it's a graph of, this graph is of SSE. Okay, so here we have graph like that. Okay, this is filled, so this is two-dimensional graph. Now our target is to find such M and C, the value of M and C, where our SSE is minimum, where SSE is minimum, like at this position, okay, where our SSE is minimum, okay. So this is M at this position. What should be the value of M? What should be value of C? Okay. So this is our target. Last time we have seen gradient descent, and gradient descent has the approach. First, randomly initialize your parameters M and C. Okay, randomly initialize your parameter M and C. Let's say we have found this parameter, then calculate the value of SSE, then calculate the gradients. Gradients will give you direction, in which direction we should move to minimize SSE. Then we will update our parameters. Update in this way, like M, previous M minus learning rate that we have learned alpha, and here should be the gradient. Okay, so here we have gradient. Okay, in the same way, we will update the parameters for the M, for the C, that we are seeing. Now maybe some of you who are interested in maths or who have done calculus in the past, he may got an idea that instead of doing this by the here the nature of the function is the convex function. So if our function is this one, in this way, here the slope of SSE, here you can say SSE on this side, the slope of SSE should be 0 at this position. Slope of SSE should be 0 at this position. If we know that, we can find out our MHC directly without going into the this type of algorithm or so much iterations. Okay. Now today's session is about that, how we can find out our MHC directly. Again, a little bit, or there will be some for some who are not comfortable with maths. So there again the maths is involved, but don't confuse with the maths. Here the idea is to give the concept, and to give you the idea how the maths involved behind the algorithms. Okay, there is not so much magic, or every algorithm has some sort of maths behind it. Okay, so here this is our today's um, session, which will be on the normal equation to find directly the values of M and C. Okay, to find the value of theta, theta is basically we are saying here uh, M and C. Okay, we have two here parameters here. For you, I can give you here idea. Sometimes the people write the equation in this way: equation of line theta 0 plus theta 1 x. Okay, just the different notation, like we have used here the notation c plus mx. Okay, so don't confuse with that. That's why they have used here the theta, so don't confuse with that, it's the same. Parameters m and c, find the value of parameters that minimize the cost function. There is a closed form solution, or in other words we can say a mathematical equation that gives the result directly. This is called normal equation. Again, we are directly finding our solution because we know that this function has a slope 0 at the minimum position. Okay, and you know the graph, like the graph like u shape have a slope 0 at this position, and if the graph is like that, it's also have a 0 where at this position also. Okay, it is 0 at this position, because we have just a graph like that convex function we have. So that's why we are doing this uh, by a closed form solution. Okay, so here we are having the function like that. If I will make this one, okay, Okay, so SSE, sum of squared error, we have this function, and this function is a parabolic type function. It is a convex function. This function must have a minima and it has no maxima. Okay, so here it has a minimum point. We are sure that it has a minimum point. Okay, and minimum point where the slope is zero. Okay, and you know about the slope, and here the instantaneous derivative, which is this one, SSE. We can calculate this slope line by using our derivatives. If I will write it, yeah, this will give you a slope. Okay, this is gradient gives you a slope. So if you want to go in detail how it gives you a slope, you can see the video that I recommended last time in the last session. Okay, so here this function have a minimum point, must have a minimum point. So minimum where SSE is minimum, this is a function that we have at this position. We have a minimum SSE. So we want a M and C at this position. So where the minimum SSE. So we will say that this M and C at the position where SSE is minimum are the optimal parameters. We can say we are interested in that where SSE is minimum, and we also have got a hint by the nature of function, by visualizing this function, by analyzing this function, that at the where SSE is minimum at the position where the derivative of SSE is equal to 0. We got an idea that this function must have a derivative is equal to 0 at the minimum position where we have a this type of curve. At this position there must be a derivative equal to 0. So we will use this technique. Okay, we will use the derivative of SSE is equal to 0. We will make it equal to 0. When we will make it equal to 0, we can find out M and C. I will show you how we can find this. Here we have SSE function. This is we have SSE function. When we will take a derivative with respect to M of this function, we will get this equation. Okay, this equation in the same way for the derivative SSC with respect to C. Now when we will make our partial derivatives equal to 0, we will go to these equations. If I will show you here, we will go to these equations. Okay, here we have put on our equal to 0. Okay, so when we have make it equal to 0, now we can calculate this as sigma xi yi x square xi sigma xi n, when we will put the values of this from our data set. And what are these values? I will show you here. Here, this is our x and y. X is actually nothing but area. This is area. This is our price. The data set that we have for training process. So we have a data set. This is area. When we will take the x square, this will be this one, price, y. So we have concatenated separate columns here, which has x square values, which has x, y, x multiplied with y, this column. This is a sigma xy. Okay, so here you can see we have sigma x, sigma y, sigma x square, sigma xy. Okay, so when we will put these values by after putting the partial derivatives equal to 0, we will get this equation. In case of when we have put the value with respect to m equal to 0, we will get this equation. And when we will put with respect to c is equal to 0 and put the values from the data, we will get this equation. When we will rearrange these equations, we will get two equations. This one equation, this one is true, second equation. Here you can say 5496m plus 164. If I will write here in this way, we got these two equations, 5496m plus 164c equal to 1042.5. In the same way, second equation will be 164m plus 5c 31.3. When we will calculate these equations simultaneously, we will go get this m and c value. Now we have gotten the m and c value where the partial derivative of SSE with respect to m and SSE with respect to c are equal to 0, where these parameters, where these derivatives are equal to 0, or in other words you can say where SSE is minimum. Okay, where SSE is minimum, we got the parameters m and c. Now we have this m and c, and you can directly write your equation. Here your y cap will be equal to 0.1358 x plus 1.806. Okay, you got this equation. Now you can say your model is trained. Okay, now you have gotten your optimal parameters or the parameter values where your error is minimum. Okay, so this is about today's session. How we have we use the technique uh, by knowing the nature of the function. We know that our function SSE is of the nature. If I write here, SSE function that we have in our that we have here, yi minus mx minus c. This function we have, it's a nature of parabolic nature, and it's a convex function. Okay, it's a convex function, this function. So we know this one. So by using this technique we have calculated we have calculated our m and c where SSE is minimum, and we know SSE will be minimum where its slope is minimum, or where its slope is equal to 0. Okay, by using this technique we have find out our m and c, these parameters. Now our library that we will use in future, in the next session I will give you a simple demo how we can use a library from the sklearn linear regression. We will use next time in the next session hopefully. So linear regression class is also use this closed form solution. Okay, also use closed form solution technique because of the nature of SSE. Because the function is convex, so don't need to you run the algorithm gradient descent. Instead, we can use this closed form solution and linear regression, the library doing this. Okay, using this technique behind this. Okay, but to improve the some you can say complexity or computation, they have tweaked some sort of calculations. So we don't need to go in the detail, but I just give you idea that as I told you that y is equal mx plus c we are using here. Somebody has the equations like that, like theta 0 plus theta 1, same, it's the same. Okay, and someone also make it in the form of like you can also write this equation in this way: theta 0 x 0 plus theta 1 x 1, and here mentioned that x 0 always equal to 1. Okay, it's also the same as it is. Okay, so in the vector form, when you will convert, somewhere you will see the solution like this, theta cap. Instead, here I have calculated manually these two equations. Here, these two equations, this one and this one, this one and this one. But somewhere you will see the theta cap like this. Theta cap is the M and C actually. Okay, so somewhere I am just giving you idea. Don't confuse with that. Somewhere you will see such type of equation. So don't get confused with that type of equation. So that's why I am telling you here. Don't need to learn that equation. Okay. So sometimes you will see the equation like that: x t, which is transpose x inverse x transpose y. Okay. So this is also the same as we have calculated our two equations. Okay, we two equations that we have calculated, it is the same like this. Just it is in the form of it is vector form, so that's why it is in this way. Okay, so we can also use that directly. In some books you will see this equation in this form. Now the linear regression, sklearn linear regression, sklearn linear regression using the same closed form solution technique, same technique, just a little bit they are using a different strategy for the computation. Okay, they learn linear regression using a little bit different technique, which is a pseudo inverse. So I am telling you these words, just if you will see somewhere these words, don't mess with that, or don't confuse with that. It's a very simple. Just there is some difference of the strategy they are using. Like they are using, maybe using in the form of vectored form. Okay, they have converted their equations into vector form. Okay, so they use the SQL and linear regression use the technique of pseudo inverse, in which they have the equation like that, x plus y. Okay, this is the pseudo inverse of x. Okay, and they used in this way. Okay, so don't confuse with that. We are good with this till now. We have find out these parameters, and here just quick recap is that we in the last session we have done gradient descent, in which we are iterating our process of updating our parameters in the way we are decreasing our sum of squared error. Okay, we are interested in the our parameters m and c, where sse is minimum. Now, in this session, we have seen that our SSE function is of a convex function, and if it is a convex function, so it should have its slope 0, where it is minimum. So we can use this information to calculate directly our parameters m and c. Okay, we have done there, and here I have given you the idea of some different equations that you may see in some different sites or in some different books, but don't get confused by that. Okay, in the next session we will use the library linear regression in the Jupyter notebook, and we will play with this small data set, so that you will get an idea how simple or how easy is to use the libraries instead of this complex maths for the students who have no idea, or who are not comfortable with the maths. So I hope you have learned a lot. If you will get confused, you can stop the video. You can you can go back and see the video multiple times. So for now, thank you.